All right, good morning. We're going to do the work power practice problems too that were assigned Thursday, and we're due Thursday night. So here we go. All right, so here we go. So the first problem, power uses, or a motor uses 1,000 watts, I should say of power. Oh, yeah. So that's totally my bad. A motor uses 1,000 watts of power over an 8-second period to move an object 5 meters. So how much work does the motor do? Okay, so let's take a look. So we're looking for work. So the equation we're going to have to use, power equals work over time, right? So we know power is 1,000 equals work over time, which is 8. So to bring the 8 to the other side, we multiply, and work is 8,000 joules. Okay. B, how much force does the motor produce? Well, we're going to have to use this equation over here. We know work now, that's 8,000. We're looking for force, and the distance is 5 meters. So if we want to solve for force, we divide both sides by 5. 8,000 divided by 5 is 1,600 newtons. Okay? All right. So that's A, 1A and 1B. All right, let's look at 2. So a piece of luggage is pulled 20 meters with a force of 100 newtons at an angle of 30 degrees. How much work is done on the luggage? So we're going to use, again, work equals force times distance times cosine theta, because there's a theta this time. So that's 100 times 20 times cosine 30. All right. So 100 times 20 is 2,000. And then we just got to do the cosine of 30. Got to make sure you're in degrees. 30 cosine times 2,000 and 1,732. All right. That's how many joules of work are done. And then if we know that it's pulled for 15 seconds, we want to find out how much power is used, we can just use the equation power is work over time, or 1,732 divided by 15. Whoops, throwing my phone everywhere. So 1,732 divided by 15 seconds. And you get 115, and then we'll just round that decimal to 0.5 watts. You can do W, or you could write out a watts. Okay. So that's 2A and 2B. All right, on to 3. So a box is pulled with a force of 30 newtons across the ground, which produces a force of friction of 12 newtons. And we pull the box 6 meters. So how much work is done on the box, how much work friction does, and then the net work. So they're going to start off both the same way. We're going to use work equals force times distance. So 30 times 6, and it's 180 joules. Okay, that's how much is pulling the box. Friction, though, is also doing its own work, because friction produces a force of 12 newtons, and it does that for the 6 meters as well. So that's 72 joules. So that's our 2 works. And then net work, just like net force, work is a vector. So we're pulling the box in one direction. The friction always acts against that direction. So if we're going in opposite directions, one force is positive, one force is negative. You know, it's arbitrary. We always like to make friction negative. So 180 minus 72 is 112 joules worth of work. Okay. If you wrote down 18, that would be the net force, because that's 30 minus 12. And you could do that. If you did that, let's say you just did that real quick, just to show you, we'll do it in color. So let's say you did it another way. You found the net work via the net force. You could do 30 minus 12, that's 18. That's the net work done. You still pulled this for a distance of 6 meters. Oh, and this is not 112. This is 118. I don't know how to do mental math in my head. 180 minus 72 is 118. 18 times 6 is, believe it or not, 118. And it's not 118 either, because again, Bao cannot do mental math. Let's try this again. Both of these again. I'm sorry. Okay. This is 180. This is 72. 180 minus 72 is 108. God. Got like rabies or something. Okay. For the second part, when you want to do it the other way, you could find the net force, which is 30 minus 12, that's 18. We can still multiply it by 6, and we still end up with the same amount of net work, 108. Okay, so 108 either way. All right, 4. So I think 4 is easiest. We're going to actually write out some equations first. So first we're comparing power and time. So power equals work over time. Okay, so notice you can think of it like fractions. Power is technically, over 1. So power and time are opposites of each other, right? See, power is on the top of one side of the equation and time is on the other side on the bottom. That means they're inversely related. If time goes up, right, if it takes more time to do a task, the amount of power required actually goes down, right? And if the time goes down, then the power required to do something goes up, okay? So this is inversely related. All right, B, power and work. So same equation, right, as up here. If the numerator or work increases, then the amount of power required also goes up. And if the amount of work required goes down, then the amount of power required also goes down. So these are directly related. Okay. All right, work and force. So for this one, we're actually not going to worry about the power equation. We're going to look at this one. Work equals force times distance. We can throw cosine theta in there too. It's no big deal. Well, now we're going to compare work and force. Well, if d and cosine theta are held constant, we can kind of ignore them. So if force goes up, then work has to go up. And if force goes down, then the amount of work has to go down. So this is also directly related. So it was inverse for A, and B and C are both directly related. All right, if you guys have any other questions, just let me know, and enjoy your Memorial Day weekends. And next week, we're going to work on energy and how work and energy are met together, and then we'll kind of start reviewing from there. And this is probably going to be the last thing we're going to be working on. We might get to one more chapter. We'll play it by ear. Have a great 3-day weekend, everybody. Stay safe, stay happy, stay healthy, stay sane. Hasta luego.